Hello, everyone. My name is Inda Zhang. I'm a research scientist at Google. Today, I'm going to talk about how to predict high-quality depth, especially for computational photography applications. These days, depth is enabling many novel applications on mobile devices. For example, the face authentication, portrait mode, color pop, 3D photo that allows you to look at the image from slightly different viewpoint, and augmented reality. Of course, depth is playing a very critical role behind all of these applications. But how are we getting depth on mobile devices these days? Let's take Pixel 4 as an example. On the backside, it has a dual camera setup on which we can run some standard stereo method to estimate some depth. And on the front side, we have an active depth sensor that shoot out some IR signals to help us measure the depth. And these depths are in general good because they are basically reflecting the correct relative location between objects showing in the scene. But if you look carefully on the depths, they are either incomplete or has quite low quality boundaries. And unfortunately, these are very, very harmful for computational photography application because over there, we wish the depth to be pixel-wise perfectly aligned with the color image to maintain those boundary visual appearance. So how can we improve the depth on these aspects? And one common answer is to use the unreasonably effective deep learning. And of course, this is not surprising these days, because everyone would think about using it. But at the same time, people also sometimes feel scary about tuning the architecture and those hyperparameters, because we simply don't know why it works, and sometimes we also don't know why it doesn't work. So today, what we want to talk about is to provide you some more controllable way to improve the depth quality using deep learning by providing some rationally powerful data. And I'm going to explain what data are we using in the next part of my presentation. First of all, let's look at the rear-facing camera on Pixel 4. Again, on the back of the Pixel 4, we have a dual camera setup that consists of two cameras that gives you two images of the same scene. And because the baseline between these two cameras, we can run a stereo between the left view and the right view. And the typical failure case for this for the stereo system is in the occluded region, where some contents of the image is only visible in one view but not the other. For example, the tip of the temple in the back. And for this region, the predicted depths are usually quite blurry. Fortunately, on the wide camera of the Pixel 4, we have a dual pixel lens that provides some additional inputs to predict the depth. There are some different formulation of the dual pixel system, but one way to understand this is that it can provide you a pair of image taken from each half of the pixel. So the baseline between these pair of image are very, very small, which is the size of the pixel. And that's why you'll see the parallax between these two images are also very tiny. And then we want to design a system to leverage both of these two inputs, the dual pixel and the dual camera, for depth prediction. And the reason we want to do that is that these two sources of information really provide complementary depth information. On one hand, the dual pixel image has very small baseline, so it has less occlusion issue, but it also has the problem to detect depth for distant area, because for any pixel which is more than 1 meter away from the camera, there will be almost no parallax between the dual pixel images. And also another issue about a dual pixel image is that there's an unknown affine transformation between the parallax to the metric depth. And this affine transformation is related with the focus distance, which is unknown in the image. And on the other hand, we have the dual camera input, which has a larger baseline and definitely has more severe occlusion issue. But on the good side is that it can still measure depth in the background. Also, there's a mask that can bring us from the parallax between the dual camera images to the metric depth. And when we design the hardware, we can place the direction to the baseline of these two systems to be orthogonal, so that we can measure the depth change along all different directions. So if you check different property of the depth you want to maintain in the output, you're going to find that these two systems are really complementary. Then we start to think of how to design the neural network architecture to fuse the two sources of the input. To do so, we first use some very standard network architecture to predict some depths out of these two sources of input. And we use very standard cost volume followed by a soft arc mean kind of architecture. And then again, there's a known affine transformation between these two. And in practice, there's going to be another spatial transformation that need to be applied on the dual pixel image in order to align with the dual camera image because of the stereo rectification. So the way we fuse these two sources of information is to first fit this affine transformation using the predicted depth, and then we sampling the dual pixel cost volume using the spatial warping together with the affine to make it align with the dual camera cost volume. And then we run some 3D convolution to refine the cost volume and then produce a low resolution disparity map. Also, as a quite standard step, we use both the dual camera and dual pixel image to refine the low resolution disparity in order to recover some high resolution details in the depth map. Here we show that with our system that combine both the dual pixel and the dual camera, it can significantly outperform the depth from either source of the input. And also here's a comparison to a state-of-the-art method that use only the dual camera or the dual pixel as the input. Again, our produced depth maintains significantly better details. Then we can run our model on different scenes, and it can successfully produce very nice looking portrait mode images. And we also compare the depths on the 3D photo application where we use our depths and also depths from previous method that use only the dual pixel or dual camera. As you can see that only with our depths, theme structure can be well maintained. For example, the circle here, and also the theme structure, the rail here. Please check our project webpage if you want to know more. And also there's a blog post that gives you more details. And also feel free to check our paper on archive to know even more about the network architecture. All right, so the first kind of rationally powerful data I want to introduce is basically to provide some source of input that can give you complementary information about the depth. And apparently there's a second part, and to know that, let's look at the front-facing camera on the Pixel 4. Again, on the front side of the Pixel 4, this is an active depth sensor that gives you some depth rely on the IR signals. And because the field of view of the depth sensor is slightly smaller than the color image, when we warp the depth from the depth sensor to the color image, we're going to see it's smaller than the color image. And that's why the depth is not complete in the border area. And also the depth is not very great near the object boundary. So the thing we want to do here is to design a deep learning architecture to produce a complete depth with sharp boundary. And of course, there are many architecture we can think about using. But before that, we need to really solve one important question, which is how can we get high quality ground truths to supervise such a deep learning system? To get the data, we first build our customized high resolution capture rate. More specifically, we reuse the capture pod from the light stage and make it into a portable rig. And then we place a cell phone in the middle so that we can take a photo at the same time using the cell phone as well as the high quality depth sensor. And then we have the relatively low quality depths from the cell phone aligned with the high quality depths to create a training data. We use this capture rig to capture data in our office with different subjects in different background, with different number of persons holding different objects. And here you can see that our captured ground truth depth is much better than the depth from the Pixel phone. It's more complete and more accurate and give us better, more signals along the foreground boundaries. Here's another example. But keep in mind that we want a complete depth with a sharp boundary. But here we still have some issue here and there. To make it more perfect, we leverage some synthetic data. To do so, we first create a high quality performance capture using the light stage, which provides us a high quality texture map that we can render high quality training data from arbitrary viewpoint. We can also put something in the background and then render synthetic data. Because the ground truth is rendered from the synthetic data is going to be perfect, complete, and with a sharp boundary. And if we train the deep learning architecture with a combination of the synthetic data and real data, we're going to get something like this. First of all, this looks much better than the input depth. The foreground depth looks quite good with sharp boundary. That's all fine. But the only issue is here in the background is not correct. And this is because in our training data, we don't have sufficient diversity in the background region. In order to find the missing part of the data, we leverage the existing large-scale RGBD data set. So here we use the data from these two data sets, the diode data set and ScanNet data set. Each of them provides quite a lot of scan from different indoor and outdoor environment. And for each camera viewpoint, it provides both the color image and the depth image. And then we use this data to create new training data. Here's an example. We pick some data from the Pixel phone and some data from this data set, and we paste the foreground objects onto this scene captures to create some new examples. So we can also composite the depths in the same way to simulate the input and output ground truth steps. To improve the image quality throughout this data augmentation process, we try different kind of blending technique to blend our capture with the image from the from those scene level data set. We try alpha blending and Poisson image blending. You probably still see some artifacts here and there, but we found that the neural network handles these pretty well. And again, the ground truth data are almost perfect. And then if we add this augmented data into the training data and then we train the architecture, we get much better depths with both good depths in the foreground and good depths in the background. And since we have quite good training data, we don't have to push really hard on the network architecture. Therefore, we use a quite standard encoder-decoder architecture. We have several encoders to extract features from different sources of input, and then the feature are concatenated and fed into the decoder. Some high resolution feature are short connected to the decoder as well to maintain the high resolution feature. And then the decoder directly gives us the output depth. In order to get better depths, here's a couple more tricks that we apply during the training. The first thing is to randomly drop depths during the training, which means in some of the training iteration, we replace the depths using all zero matrix. And in this way, we want to really encourage the network to learn better from the color image, especially to leverage those edge information and maintain them in the final output depths. And the byproduct is that this model can also work robustly when the depth is not available. Here I show two examples where we test our model with and without depth. As you can see that even without the depth, even with only a RGB image as input, the output depth is still quite reasonable, especially in the foreground. While in the background, it doesn't have any sense, but the foreground depth seems to capture the person quite well. And another trick is to randomly shift the depth during the training. This is because that in practice on device, the calibration between the depth camera and the color camera may not be perfect, which will introduce some level of misalignment between the depth and the color. So during the training, we manually add some shift between the depth and the color. And therefore, during the testing, we found that our deep learning system can successfully fix the imperfect misalignment. For example, here in the input, we can see there are quite a lot of misalignment, but in the output, the network learns to align depth with the color image. We then use this great depth for some of the computational photography applications. The first thing we try, again, is the portrait mode. Note that the portrait mode can also be achieved using a foreground-background segmentation. For example, you can blur out all the things in the background, but then you're going to lose the chance to tell the difference in the foreground. However, if using our depth, we can really pick which person to focus on, like here. We can also use the depth to enable this kind of relighting toy examples. We also use the depth on 3D photo. Again, using the segmentation, you can understand the scene as two plane, with the foreground plane containing the person and background plane containing the scene. But again, that won't tell you the variation in the foreground. For example, the relative motion between the hand and face, which can only be achieved using our depth. And sometimes the segmentation only focus on the person part and will make some mistake on handheld objects, while with our predicted depth, they're going to be okay. And again, with only the segmentation, there's no way to figure out the variation in the foreground. While using our depth, we can successfully simulate the relative motion between these two persons in the foreground. So for the second part of this rationally powerful data, I guess you probably already have the answer, which is to provide a high quality training data as the supervision. So today, overall, we showed that instead of trying very complicated deep learning architecture or tuning those hyperparameters, providing good data is also a very effective way in improving the depth quality when we use the deep learning. And also in practice, this process is more controllable and interpretable. Thanks for attention, and feel free to drop me an email if you have any questions.